We will now use this vector formalism to look at position, velocity, and acceleration, and how we define those kinematic variables as vectors. Let's start with position. Position now has a symbol in terms of a vector, and the symbol that we use is r. In terms of its components, the x component of r is just x, and the y component of r is y. And so we will almost exclusively use the components, and you will rarely see the symbol r. Now, before in one dimension, to describe position, we had to make two choices. Similarly, now we still have to make two choices. The first choice is an origin, and that's still the zero position, that's no different. But instead of one positive direction, now we need to choose what's called a coordinate system. And this is simply a choice of an x-axis and a y-axis with the corresponding positive directions for each of them. Before, in one dimension, we had other quantities, and the same quantities can be measured as vectors. Displacement now gets a symbol delta r, where r has the vector symbol. This is no different than what we had before, except that we're using our new vector. And the formula is no different. Delta still means change, so the displacement is equal to r final minus r initial. We can also talk about distance traveled, but again, distance traveled will not be used that often because it still has the same issues as in one dimension in that it can be tricky to calculate and often requires calculus. Let's go ahead and look at this example. In this example, we're given the position of a particle initially and at the end. What we want to find is its displacement. So we apply our formula, delta r is equal to r final minus r initial. And our final position, well, we just plug that in as a vector, 7i plus 5j. And now we need to subtract off the initial position, 3i plus 4j. Now subtracting this is the same as we saw before, where we subtract component by component. And so the x component is simply 7 minus 3, and the y component is simply 5 minus 4. In the end, that just gives us 4i plus 1j. And as I said, many of the questions will be taking the components and trying to answer it into a real-world problem. Whereas calculating its displacement is not something you very often hear, you might hear somebody ask how far is the final position from the initial position as in part B. And to do this, what we're really being asked is to find the magnitude of this displacement. And to find the magnitude, we simply use the Pythagorean theorem, in this case the square root of 4 squared plus 1 squared, and that tells us that our final position is 4.1 meters away from our initial position. Now let's look at velocity. Velocity gets the same symbol v, but this time with a vector sign. In terms of its components, v gets subscripts, and so the x component is v sub x and the y component is v sub y. Speed, which in one dimension was the absolute value, is now the magnitude of the velocity, which makes sense for vectors. And so its symbol gets the vector symbol for magnitude. Average velocity hasn't changed. Its symbol now just gets a vector sign, and the formula hasn't changed either. All we're looking at is displacement, now defined as delta r over delta t. Let's look at how we apply this in a problem, and I hope you see that it is not that different than what we did in one dimension. It's almost like replicating two one-dimensional problems. So in this case, we have a particle at an initial location, and it travels to a final location in 5 seconds. We're asked to find its average velocity, and so we start by writing down its formula. This is simply r final minus r initial over the time, which was given to us as 5 seconds. Now if we plug in our final position, 7i plus 5j, and we subtract off the initial position, 3i plus 4j, well, in the end, subtracting is nothing but working component-wise with subtraction. And so what we do is we subtract off 7 minus 3 to find our x component, and 5 minus 4 to find our y component. This gives us 4 for the I and 1 for the j, and when we divide by our time, it works out to be 0.8 meters per second I plus 0.2 meters per second j. And as you can see, in the end, what we really did is we just found the average velocity in the x component, which was 0.8 meters per second, and the average velocity in the y component, which was 0.2 meters per second, and we wrote them together in a vector using our component notation. Finally, for acceleration, it gets the same symbol a, just with a vector sign. And in terms of components, we denote the components with subscripts, so a is equal to a sub xi plus a sub yj. Now, the important thing to realize with the vector formalism is there are some changes here. And this warning tells you about one that you need to be careful about. If the direction of the velocity changes, then the object is accelerating, even if the velocity's magnitude is constant. Because with a vector can either change by having its magnitude change, or having its direction change, or having both of them change. And this will be important later on. Oftentimes students get confused because they see that the speed of an object is not changing, which is to say the magnitude of that object's velocity is not changing. However, it's changing direction. And an important example we'll see in the next chapter is what's called uniform circular motion, where an object travels in a circle so that its velocity is constantly changing direction, even though its speed is staying constant. Other quantities related to acceleration are similar to what they were before. We can still talk about average acceleration, and its symbol is still essentially the same, just with the vector sign, and its formula is still essentially the same, except that we're using delta v, where v is a vector. So let's look at this in this problem. In this problem, we are given the velocity of a ball as a function of time. What we're told is that the velocity in the x component is simply t, and the velocity in the y component is 2t. So let's use that information to calculate its initial velocity in part A. So if we plug in t equals 0, well, the x component, t, substituted in with 0 becomes 0, and the y component, 2t, well, 2 times 0 is 0, and so our velocity is 0i plus 0j, which is to say there is no velocity. In part B, we're asked to calculate its initial speed. Well, that's just the magnitude of this velocity, but since the velocity is 0, its magnitude is also 0 meters per second. In part C, we are asked to calculate the average acceleration, and we use the formula that we were just given. Change in velocity over change in time. And this is v final minus v initial over the 2 seconds. And again, now we need to plug in the final velocity, which was at 2 seconds, and we do that by using our formula. So we plug in t equals 2 to get 2 for the x component, and we plug in t equals 2 to get 2 times 2 is 4 for the y. We then subtract off our initial velocity, which was 0 for the I and 0 for the j, and divide by the time. Simplifying this, we get 2i plus 4j over 2, which simplifies to 1 meter per second squared I plus 2 meters per second squared j. And I hope you can realize that all we really did was to find the average acceleration in the x direction and the average acceleration in the y direction and put them together as components of a vector. In part D, we're asked to calculate its velocity and speed at 2 seconds, but we already had to find the velocity at 2 seconds in the previous problem, and so we can just rewrite that here as 2 meters per second I plus 4 meters per second j. And then to find its speed at 2 seconds, that's just the magnitude of that vector. So we apply the Pythagorean theorem. It's the square root of 2 squared plus 4 squared, and that comes out to be 4.5 meters per second for its speed. And this again gives a good example of being given something in terms of components and being asked for a real-world type question, speed, which in this case has to do with the magnitude of a vector. This will be quite representative of how we'll work with components in the future, even if we decide not to use the vector formalism.